Professor Oja ma'am and Pritikarna ma'am for inviting me to this particular workshop. So today we are going to discuss about some of the concepts of object detection. Okay, so before going to discuss or before diving into the concept of object detection concepts, so let's try to correlate how these particular object detection concepts are, how much similarities are there with the image classification problems. So as majority of the people are already aware of that, what is meant by an image classification problem and what is a working principle of it. So let's brush up these things so that it can be correlated to the concepts of object detection. Let's assume here we have given the sample query, that is the image here. Now we are going to ask a machine to detect or recognize what this particular given input is. Then this particular image will going to pass to the network, and the network will going to have some training and the corresponding weights with some loss functions. It is going to give you the given input is belongs to the cat category, or the given input is belongs to the dog or whatever, depending upon the properties of the given input. But if you will try to see and analyze here, this is an image where the single object is present. And for this particular image, you are trying to get an output is its category. So now we are calling this as an image classification problem. Now, can I call this particular problem as an object detection problem? Because there is an object called a cat is present in this image, and my classification output is also belongs to the same thing. Now, how come these particular object detections are different than the image classification? Because in these two cases, the things are remain same. Because in the image classification, if you try to analyze, here we would like to take a decision on the entire image. Whether the size of the object is not matters and position of the object is not matters and its orientation, these are all not matters. Whether the object is present, if the present, then what the particular object is. That is called simple image classification or image recognition problems. Now, as you can able to see, if you can little bit extend as with this example, this is my input and this is my desired output on the right side. Now, what is the similarities and what are the extra things which you can able to identify as compared to our previous slide? So if you can able to see, this is a big image of size m cross n, where there is a bike, there is a person, and there is a road. If you can able to see in this image, we have a curved road is also there, and person is trying to ride a bike. But in the image classification, if you'll ask this particular image as an input, what type of the class this particular image is belongs to? Can we able to say? Because in this image there are more than one objects were present. What is that? A person is there and there is a bike is there. Now, if you're going to pass this as an image as an input to a classification problem, now this particular model may going to confuse which particular class it belongs to. But whereas if you can treat this particular problem as an object detector, because there is a more than one object is present, so the outcome will be like this. So whenever we're going to pass this image as an input, then we are going to get the output in this particular form. So the yellow color bounding box is going to representing about a person. The other color bounding box is going to represent as a motorbike. That means whenever we have a more than one object is present in a given input image, now the image classification problems are going to fail, are going to get confused. So the extended versions may going to help us to get the desired or robust outputs. So let's assume this is this hypothetically, whenever you would like to test a model, how the things are going to be happen. Because now if you can able to see in this particular image, there are more than one object were present. There's a horse, the person, tree, and many more. House, grass, many things are present. So how we are going to getting this output? Let's assume how to make the training, those things we will going to discuss slowly later. Let's assume hypothetically, if you would like to test with this type of an image, what will going to happen? So whenever we're going to test with this particular unseen data, so as you can able to see, this is a bounding box here. The particular bounding box is going to be detected the person. Similarly, there is a person, because you are here, we are trying to develop an algorithm for the person detection, for example. But now you see the third bounding box. The first detection is a person with 90% of the confidence. There is a second bounding box is having 60% of the confidence. But the third person is having 20% of the confidence, but it has detected the tree. So what is meant by a confidence here? Why we have here used as a confidence term? Because if you can able to see here, the algorithm, whatever you are going to train, because this is some portion of the image, we are going to take a decision, not on the entire image, right? So this is an image of M cross N. The bounding boxes, whatever you are able to see it here, the sizes and shapes of the boxes are something different. But as you can able to see, the small bounding box, that particular bounding box, you may can treat as a small patch of an image. For that image, for that particular patch, how confidently that particular model is going to recognizing that particular object. So this particular example, the algorithm is trying to talk about the 90% of the confidence. Now, how you can able to calculate the confidence? Because in our training, during the training process, we have a corresponding ground rules, or it can be called as a labels. So as you can able to see here, there are many other people are there. We have already created the ground rules for this. But whereas the algorithm has detected or predicted these particular orange color bounding boxes as an output. So as you can able to see it here, the detected orange color bounding box is trying to be overlapped with my ground truth. So here the overlap ratios are much good, right? Similarly, as you can able to see, this is the wrong predictions. So based on this, the overall algorithm predictions we are going to calculate. This is just it is just a overview. But now, what are all the challenges are there for developing an algorithm? Whereas compared with the image classification problem, because as we knew, the image classification problem is like passing an image and get the desired output. But what type of limitations, or what type of the assumptions we are trying to make before developing an algorithm is also matters. So if you try to see it here in the object detection, here we might have a more than one object may present, and size and shape of the objects may differ, and its locations also might be different. So multiple objects can be present in a single image. That is the first challenge. Second thing is multiple types of object. That means the available type of an objects may not belong to the same category. It may belong to different categories. As you can able to see it here, this is a combination of cat and dogs. So in this example, we have one cat and two dogs are there. So here we can have more than one type of a category may present in a single image, and the number of objects are present in the single image may also be more. That is another challenging part. Third interesting point which we need to observe is that whenever we are trying to talk about any of the classification problem, in general, we will try to handle the image sizes of 224 cross 224 or 128 cross 128, and depends upon the application. But whereas comes to the object detection concepts, the image size is much higher than the classification problems. For example, here the sizes are 800 cross 600 or 680 cross 680 and so on. So that means the number of pixels we are going to process is much higher than the image classification problem, other than the two challenges whatever we have addressed earlier. Again, let's try to correlate and simplify the problem so that we can get some confidence in object detection concepts. So if you can recollect the procedures of an image classification problem, what type of a procedure we are trying to follow? This is an image. We are trying to pass to some network. Here the network can be anything. That is up to our choice. Maybe VG16 or RetinaNet or ResNet, GoogleNet, whatever it may be. So whatever the image is there, that image we are going to pass it as an input to the network, and this network is trying to give you some latent vector that is called the output vector. So if it is a VG16 and 4096 is a feature vector for the architecture. Now for the classification, what we are trying to do, these 4096 features, we are going to pass it to the fully connected layer. Let's assume that as if this is the ImageNet classification problem, image classification problem on the ImageNet dataset, then we have 1,000 classes. So in the fully connected, we can use the 1,000 classes. So we can get the 1,000 probabilities with the help of the softmax function. From there, we are going to get the scores, and wherever in which category we are getting the highest score, it means that the given input is belongs to that particular category. That is the image classification problem. I hope you're already aware of it, right? But what about this particular, now this is image classification problem, right? Now I'm going to ask you a question that, okay, the given input is having a single object. In addition to the type of the object, I also need to know where that particular object is. I hope you could able to get my question, right? The first question is that the simplest problem is that let me pass an image with a single object is present in it, passing to one of the architecture, popular architecture, get the desired output, pass it to the fully connected and softmax so that we can able to get we can recognize what the given input is. But what if I want to know the position of that particular object is in addition to its type, in addition to its category? Then we need to go for the object detection concepts rather than the classification problems. Because in this object detection, what we are trying to do, of course, yes, we are going to classify or recognizing what that object is. In addition to that, we are trying to figure it out its location. That is called localization. So the object detection can be named as is a combination of classification and localization together. So as you can able to see it here in this particular diagram, the output feature vector, what are the latent features are there with us. If it is a classification, we are passing to one of the softmax function. If it is a location, the location means the size of the object is also important and its positioning is also important. So as you can able to see in the left side image, there is a blue color bounding box. So the blue color bounding box is having 4 values. Those values are height of the object, width of the object, and coordinate. So this is not the corner, this is the coordinate of the object. That is called center, the presence of the object. That means for this particular bounding box, this is a center, that is a x comma y, and height and width. So in addition to this particular classification problem, I also need to learn its location, that is called bounding box coordinates x comma y comma w comma h. So these latent vectors called 4096, we are going to pass it to predict these 4 coordinates. So whenever we are going to predict something, here we can use this particular problem as a regression problem, because this is a classification problem, first part. So second part is a regression problem. Here we are going to figure it out some values, continuous values. So as you know, to identify or locate the positions of the particular object, these four values we need to predict. So in order to do that, we need to use one loss function. So here you can use either L1 loss or L2 loss. Whatever the regression problem we might be studied, similar type of loss function we can do it, because we already have a corresponding ground truth results. We have our label, and now we are trying to predict in this 4 coordinate value with the help of the L2 loss. So you may can think that this particular given input image is for the object detection where the 2 tasks are happening. The first one is classification problem. So in order to get the classification, proper learning for the classification, there should be a loss is also required. Maybe we have used a softmax function. But in addition to that, we also would like to know the location of the object. So there should be another loss. But while you're trying to train your model, these multiple losses, we can't able to use it individually to train the model. So we need to combine these 2 together to form a single loss. And this loss we are going to use it to train the entire network. So if you would like to see this particular thing in this example for the object detection problem, One is classification problem and location is problem. One is a classification loss and another is a regression loss. So here we would like to do two different tasks together. So it can be also called as multitask class. Because here the one loss is for the classification, one loss is for the regression. So this can be called as a multitask loss. A single loss, which is a combination of two different tasks. And these two tasks are together performing to estimate the final objectives. So if we want to know an object to be detected in a single image, only 4 values are required for us. That is called X, Y, width and height in addition to this particular classification problem. What if I have a more than one object is present? So in this case, the detection of the object is much easier because it is a very simple problem, because a simple classification problem, by adding some extra loss function, the problem can be resolved. But in this case, if we have a more than one object is there, then what to do? That is the first question. If it is a more than one object is there, how many new parameters to be learned is the second question. The third question is that parameters and the size of the objects and quantity of the objects, is it matters for the training the model? So these all factors motivated us to go and see about in details about the object detection concepts. Let's see about in the second image where we have three different objects are there. 1, 2, and 3. So as we have three different objects are there, where the 2 dogs and 1 cat is there. So there are 12 parameters which we need to learn. 2 coordinates for the dog and height and width. Similarly, for the second dog, its position and height and width for the bounding box. Third one is for the cat category, its position and height and width. So what if this particular last one where we have a very many objects are there? So there are many parameters we need to learn. So as you can able to see it here, each image needs a different number of outputs. For the one output is 4 number, second one is 12 number, the last one is have many numbers. So you may can now think the first part is not a problematic. Coming to the second part, just we can hypothetically think about the finite number of objects, maybe 3 or 4, let's assume. How can we train our model? Any ideas? Let's assume, try to correlate with your image classification problem only, then share your views. How can we train this particular second image? Any ideas? Okay. The first thing is that in this case, we have only one object is present in a particular frame, right? Then recognizing that object is much easier. But the same case may not going to be helpful for the second image, where because more than one object is there. What if? So what if I am trying to get some portion of the image as an input and pass it, sorry, some portion from the input image, I'm going to use it as an input to the model. Means let's take this particular small portion, like the bounding boxes, so the some portion that is a blue color part, you can able to see it here. Now what we are trying to do, I will try to take some portion as an image. That image I'm going to pass it as an input to the CNN architecture, because in this case this is a small patch, right? This particular patch can also be treated as an image, even though this patch belongs to a bigger image. Now we can take this patch and pass it to the one architecture. From there we can able to recognize what the particular, is there any object is present in the particular patch or not. So in this case, the patch belongs to background. Similarly, you can shift the patch and you can take one different patch where you can able to see it now. This is a small portion of the image where only a single object is present in this example. Now this particular small patch I'm going to treat as an input to the CNN architecture, and the CNN architecture has given the output as this particular image belongs to dog category. not for the cat in background. And the same procedure we can able to repeat it for the entire image, right? Now, by doing this approach, what are the problems you have identified? By observing this procedure, what type of the questions generally we may going to get in our mind? Any ideas? Please share. So I hope this overall idea you might be got it, right? I have an image with more than one object. Now I'm going to take some portion of the image and passing that as an input to the CNN model so that it can able to give some desired output. So this is something like a classification problem only, because I'm not going to use the entire image, some portion. The problem here is that what could be the size of the bounding box? One object size is much bigger, one object size is much smaller, and so on. So how many number of these how many number of these patches are portion of the images we can able to get from a single image? So these are all the further challenges. Let's try to think about it, because as we knew, this is one portion of an image we can keep as an input to my model. Can we able to give a guarantee that same type of a window size may going to help us to detect all the objects? If we try to observe in the same example, let's assume the first dog size is much higher, right? It's much bigger. But whereas the second dog is very smaller one. First one is very bigger one. Third one, cat, is having different sizes. Now, how can you able to get this exact shapes from the each and every image? That is very challenging issue. In order to handle that, we can take the help of this sliding window. So what we are trying to do with the sliding window, the same concept is remain same. The sliding window will going to help you to get some portion from the image and pass it as an input to the CNN architecture to for the classification or recognizing the problem, recognizing the type of the object. But the question here is that how many number of such sliding windows is required? How many such type of patches of image we are going to extract from a patches we are going to extract from an image is a big question. How many it is possible? Let's take this example. Here the W and height H are the width and height of the image. Width and height of the image. Let's assume here we are trying to take a sliding window size which is equal to the height and width of the image. That means the sliding window size is as equal to the image size. Then how many number of patches can be formed? Only one, right? Because W and small w are going to be cancelled out. We have only 1x1 image. That means we have only one window. That entire window we are going to use it as an input to the CNN model. Whether that particular window is good or bad is a secondary. So how many such type of windows can be possible is matters, right? Third thing. Now I don't want to consider the size of the sliding window is equal to the height and width. I would like to consider window size is 1. So what are the window I'm going to consider? This height and width is 1. So whenever this height and width is 1, 1 and 1 is cancelled out. Then what it means? The total number of possible sliding windows is equal to the image size, because each and every pixel we are going to consider as a sliding window and we are going to pass it to the CNN model. That means by this particular concept of sliding window, we make an able to get many number of patches from an image. That is not a proper solution. Reason is not only to get the complex possibilities. It is also challenging because each and every possibility we are going to pass it as an input to the CNN model. So as you can able to see it here, whenever we are going to considering about this sliding window, total number of sliding windows here, if the given input size is 800 cross 600, the total number of possibilities are 58 million. So there might be a little bit confusion on the sliding window. Let me repeat this again. Let me repeat this again. Here, the dog size here is much higher, and there is another dog is a smaller size. That means that we have a category of dogs with different sizes, right? So as we initially assume that one patch of an image is required to pass it as an input to the architecture so that it can able to recognize, right? Now, what could be the size? There are n number of possibilities are there. The first possibility is that I may consider each and every pixel as an input, useful or not, secondary issue. Each and every pixel we can consider as an input. It means that the size of the window is 1 cross 1. So whenever you are going to use size of the window is 1 cross 1, that means total number of possible sliding windows are is equal to the image size. The total number of pixels, how many is there? Those many number of windows are possible. Now I would like to take the sliding window of size 1 cross 2. I may can take the sliding window of size 1 cross 2. That is also possible. So like that, how many number of possibilities are there in this entire image? With the overlapping manner, there are many. I may can take the 1 cross 3 is also one sliding window. 1 cross 4 is also sliding window, and so on. Like this, the total number of regions we can able to get with the sliding window concept are 58 million. So what we are trying to do, we are trying to get a regions from the image. So k number of regions we make able to extract, and that each region, each patch of an image we are going to consider as an input to the architecture. Now again, you assume, as we know, VGG16 or any of the CNN model are very complex. For example, hypothetically, you can consider VGG16 will have almost 134 million parameters. So here we have total number of regions are 58 million. So how complex your model would be? So by using this particular simple region proposals with the help of this sliding window, the object detector model is too much of complex. So we need some alternative solutions to handle this. Here the problem is not the object detector or classification model. Here the problem is the region proposals. How many number of regions to be proposed? If you can able to find a solution for the finite number of region proposals, then there could be a chance that the object detection concepts can be feasible as compared to this basic idea. So as you can able to see, there are many number of regions can be there with the various sizes. And for each and every region, we need to pass it as an input to the CNN model to get the desired output. So here you may can get one doubt that for any CNN classification problem, the input sizes remain same. Let's assume here I might be considered the input size is 224 cross 224. That is possible, right? Because for the CNN model, the input sizes remain same for the entire architecture. Here we are trying to use k number of regions. So we need to normalize those particular regions in such a way that the CNN model should not, the architecture should not be get hampered. So this is one observation. Now, how to solve this particular challenge? So in order to solve this particular challenge, we have a concept called region proposals. Instead of infinite number, let's come to a finite number proposals. So the initial concept of region proposals they have introduced in long back. So where the traditional CNN algorithms have used, by using this region proposal concept, instead of giving infinite number, it is going to give you a 2000 regions. So what could be the tentative idea of this particular concept of selective search? Let's try to observe. So we need to get the finite number of regions rather than infinite number. In order to get this finite number, we can use the concept of selective search. So in an image, if you try to observe, we have a background that is called uniform and non-uniform regions over there. And there could be some edges and some concepts, right? In the selective search, we are trying to find or figure it out the possibility of the object. Here, is there any possibility of the object is there? No. Here is a grass region, right? Is there any specific object is there? No. That means in this particular region, we don't have any specific object. That means there are no edges, much fine, extreme edges were not present. So these regions are not at all useful for us. Like this, we can have edge detection concepts, and then we can rank them wherever we have a majority of the changes are there, as you can able to see on the right side, with the different sizes and shapes of the regions, we can able to get the many number of regions can be there, but we are going to filtering out to take the top n number. Maybe here the 200 regions we can consider, as you can able to see on the right side. So now, as you have this particular regions, selected number of regions, for that each and every region, we are going to pass it to the further models to recognize what type of an object it is present in that particular region. As you can able to see it here, this is a no object region, this is a ball, this is a flag, this is a person. So in this example, we have 4 categories are there. So each and every region, like here in this case, 2000 regions are there. So in the previous case, we have a 58 million, right? Now this 58 million is trimmed down to 2000 regions only. That means your CNN model, only these 2000 small patch of images are going to be passed as an input to the CNN architecture to get the desired output. So as compared to the previous concept, with the help of this selective search, that complexity has been reduced. As you can able to see it here, this is the person category. We got this classifier as person. The second one is for the flag. It belongs to the flag. Third is ball. Last one is no category. So it belongs to none of them. So as compared to the previous concept, now with the help of the selective search, the complexity has got reduced. This is the traditional part. So if you try to observe here, what we are trying to achieve out of this, because here not only detecting the objects, also the position, right? In order to get the position, here we need to learn these things, as we have already discussed, width and height, that is called bounding box information we need to learn. In addition to that, the position, that is called X, Y. So that is a basic flow of the object detector concept. If you have any questions till now, please, you can ask me. Then we can solve those questions, then we can move ahead. Just for a few seconds, I'll wait. If you have any questions, please put it in the chat box. Fine. So the popular architecture for the object detector initially is the RCNN, because as here we are talking about this region CNN models, because the previous concepts are traditional. Now we are coming to the deep learning model. So again, we are trying to take the help of the selective search here. The given input is there. From the input image, we are going to get the regions, selective regions, that is called 2000 regions, with the help of the traditional approach. Now for the each and every region, wrapped down to the some size 224 plus 224, because as we have already discussed that for the CNN model, we should have a same size. Yeah, this is a nice question. The regions are identified by the model itself or part of pre-processing. So in here, the region proposals here we are considering as a pre-processing technique. That is what I told you, that this region proposal concept, here we are going to use a traditional algorithm. So there are many different region proposals or concepts are there. One of the popular one is the selective search. There are many variants are there. This is done without using any of the learning algorithm, by using some traditional concept. So this is a pre-processing. From a given input image, we are going to get the regions. Many number of regions we will get it, but there we will going to take some top n number of regions only. the top n number of regions we are going to consider as a region proposals here. So this is not part of the algorithm, it is a pre-processing step. So in the RCNN, that what are the given input image is there, that image initially we are going to pass it as an input to traditional algorithm. That traditional algorithm that is called a selective search, it is going to search the regions where the possible objects are present. In this example, 2000 regions. Now of different sizes are there for sure, right? So, and all these sizes are reshaped to 224 cross 224, because here each and every region we are going to consider as an individual input. Now for each and every individual input, you can pass or use as an input to the CNN architecture. Maybe it can be VGG16 or ImageNet or whatever. You can choose anything. But as per this particular paper, they have used ImageNet pre-trained, but you can use anything. So for each and every region, pass it to the CNN. CNN will going to give you the what output that particular class is. It will go to predict the class. In addition to that, as we have already discussed earlier, in addition to this class, we also need to learn 4 parameters that is called its bounding box information. So here we have a bounding box information that's called TX, TY, TH, TW. So now you can think about it. You have a ground truths because you know the objects, you have corresponding ground truths. But as this particular region proposes is an selective search approach is a conventional approach, as it's a pre-processing technique. Not necessarily each and every region what are the selective search has proposed, it is exactly aligned with the object. There may be a small disturbance might be there for sure, right? In that scenario, how you can able to adjust to get the accurate results? That means there is a little bit shifting or translation or some modifications in the regions are required. What are the regions it has proposed? There should be a little variations might be required for the proper loss calculation. So in order to do that, there is a small 2 steps they have introduced that is called translate relative to box size and log space scale transformations. So here the what are the region proposals we have that is called PX, PY, PH, PW. That means a region proposal is going to give you the 4 values: height, width, and its coordinates, possibility of the object. And transform is nothing but here TX, TY, so on. You're trying to expecting the output is called BX, BY. Here the transform is nothing but you're trying to make small, little bit, changes slightly. So what we are trying to do the bounding box, in the bounding box, whatever the region proposal you got it PX, you're trying to multiply with PW into TX. That means here there is an image, I guess. Okay, no problem. This is an image that is called width and height, and this is called X comma Y. I'll explain here itself. So this is a bounding box. Let me use some different color. This is called width, this is called height, this is called X comma Y, right? So here, what are the proposal we got it like this. Now we are going to translate this particular bounding box a little bit right side or left side. How we are trying to translate? The initial X is this one. This particular position we are going to shift. How much you are trying to shift? With the corresponding width. Whatever the width we got it, we are trying to shifting this bounding box a little bit left side or right side with the help of little transformation parameter. So the bounding boxes are little bit shifted here left and right to get the proper detection. So this small variations is not a learning part. It is small tweaking to get the desired output. Because these region proposals were not part of the algorithm, it is done as a pre-processing technique. So the small variations can be required to get the desired output. So this is the RCNN model. But what is the complexity here? For each and every input image, we are getting the region, and for each and every region, we are going to use a CNN model. Even though it is a finite number of regions, we got it, but still 2K into whatever the ImageNet classification or VGGNet parameters, 134 million parameters. So this is very complex. So the model may properly can able to recognize the objects, but there may be a chance that there is a chance that it is much slower. Now the question comes here is how to speed up. How to speed up? In order to speed up, the concept came is called fast RCNN model for object detection. So if you try to observe the procedure is almost similar in the fast RCNN model, but there is a small difference is there. The small difference. What was the difference? Whatever the region proposals are there, that we have done immediately on the input image. That means whatever the input is there, we have passed to the selective search. It has given the 200 regions. From that, we have done the CNN algorithm. But in the fast RCNN, what are the input is there? First, you pass it to one of the CNN architecture, some portion. We can use it as a backbone model. So whenever you're going to pass this particular input to a CNN model, the CNN model can able to extract some meaningful information or interpixel relations. Some feature learning can be done initially. Instead of blindly can apply in selective search, first we can use some of the popular algorithm as a pre-trained model, or for the transfer learning, maybe you can consider that could be used as a backbone model. So by using this backbone model, what we can able to get? We can able to get the proper features can be extracted. Now, whatever the resultant of the CNN architecture is there, that is called response, architecture response, whatever it might be there, that particular architecture response or that response can be passed to the selective search algorithm to get the regions. So what is the advantage of this? Majority of the complex issues of the CNN has now got resolved. But of the 134 million we have initially discussed roughly, that part has done only once here. But in the previous case, in parallel, we have to run this. But in this case, for a single image, only one time we can do the CNN algorithm. Then what are the output response you got it? That particular response you can pass it to the selective search to get the 2000 regions. So what are the regions you got it? You can apply the same procedure. Just you can research that particular regions, or what are the features we got it, and those features we can able to pass it to the some portion of the CNN. Because what are the CNN architecture is there? We are not going to use the entire CNN architecture here. Why we are not going to use an entire CNN architecture? If you try to recollect the classification problem, let me show you this. If you try to recollect the classification problem, this is the input, this is the output. After this, we can have a fully connected layer and softmax function. I hope you might be remember this, right? So this is a softmax function output is depends upon the number of classes, right? But if you are unable to use the entire architecture here itself, the resultant output will be finite number of values, whether it can be 4 classes, if it's a 4 classes, 4 values, if it is a 1000 classes, 1000 values. But that is not our case. We want a features. How to get the features? Instead of blindly using the entire architecture here, we can split this architecture into 2 parts. Some portion of the architecture, you can use it as a backbone. The rest of the architecture, you can use it as a, you can use it the rest of the architectures after the region selections. So as you can able to see it from this here, what are the images there? Initially, we got the image features here by using the CNN architecture. Then we got these particular regions. And at the end, very finite number of layers we can use it to use from the per region network. So the total number of complexity has reduced. Once the CNN architecture is there, obviously the 2 classes, two different things, 2 losses we need to learn. One is for the classification, another one is for the regression for the bounding box. That procedure is remains same. What is the advantage here? That particular complexity has now reduced. So as you can able to see it here, most of the computation happened in this particular backbone. So you have utilized that in the beginning itself, and very lightweight computations are going to be happen in the last layers. So you can use that in parallel. So that is the advantage of using this fast RCNN model. So not necessarily for this algorithm, you can use it for anything. Like initially, the majority of the features you can use it as a backbone, and the rest of the portion you can use it as a region learning or object detection concepts, where here the one is small, tiny, shallow network is there. Now, what are all the further challenges? Of course, yes, this algorithm has computationally cheaper because the majority of the things have done only once here. And of course, yes, by using this particular backbone model, your output will be somewhat fruitful because the model could able to already learn the features. So what are all the questions may come here? If you try to observe here, what are the output of the features you got it, and those features you have passed to the selective search, that is also fine. But after the selective search, we are going to resizing the features to 224 cross 224. But this is the entire algorithm, right? This is the entire CNN algorithm from here to here. But in the previous case, you will observe here, the challenge will be not there. Why? Here, the previous case, there is no issue because whatever the region is there, that region is already cropped and give it as an input to the CNN architecture. And this CNN architecture is not broken into two parts. Once you pass the input, get the output, and whatever the loss you are going to get it, this model is going to be trained properly. There is no issue at all. But whereas in this particular fast RCNN, what are the single architecture is there? We are dividing into two parts. One is for the backbone, another one is for the region of interest proposal method, right? So here you're trying to resizing it. But while you're trying to do the back propagation, how to handle that? There is a dimensionality mismatches are happening. So in order to handle that, we are going to have look into two different concepts. In order to handle that issue, we have two problems. What's there? One is the region of interest pool. How this region of interest pooling is helpful. Let's have a look. This is my image. As you knew for the CNN algorithm, once you're going to pass it to the CNN algorithm, CNN will going to give you some output, right? So output in terms of what? After using some couple of convolutions with poolings, we may can have 512 convolution layers. After pooling, we may can come to 20 cross 15. So just you may can divide this 640 upon 20. 32 times it has downsampled. 32. So whenever you are going to do a continuous convolutions with the corresponding poolings, the given input size of 64 cross 480 has 32 times downsampled and got the result as 20 cross 15. So this patch is the single image. So this is the one image. This patch is trying to representing this. Like this, we have how many number of features are there? Those many number of filters we have applied. In this example, there are 512 filters are there. So this entire representation is talking about the after backbone, what are the output you got it? We are talking about this. After convolution, what are the output we are going to get it here? That is the size here. So after CNN, we got the output. The image features here is got 512 cross 20 cross 15. Now we need to project it because after CNN, we are going to reshaping it and use it for the further training, right? So here we need to project the proposals onto the features because the given input regions and the after convolution features, there will be a small difference. So how we can able to project them? In order to project them, we can able to take the region of interest pooling concept. So as you can able to see it here in this, these are all the 512 features we have. Let's try to take the few features of size 5 cross 4 in this example. Let's try to do the pooling concept. Whenever you're trying to do the pooling concept of 5 cross 4 into 2 cross 2, because this is a here we have a 5 cross 4 region like that 512. Now I want to reduce this 5 cross 4 into 2 cross 2. So how you can able to get the 2 cross 2? Simply you can able to do some pooling concept here, maybe with the help of the quantization. But if you try to observe here in this pooling concept, it can be divided into 2 cross 2. What are the 5 cross 4 is there? It can be divided into 2 cross 2, right? But you try to observe here in this, the problem is, of course, yes, the 5 cross 4 is divided into 2 cross 2, it's fine. But here the regions should be of equal size. But here we have a regions of different sizes. One is with the 2 cross 2, another one is 3 cross 2. So this is not correct, right? That means what are the regions we are going to get it that is not in a properly aligned. So how to do it? In order to do that, there is a concept called region alignment. That is called region of interest alignment. So in the region of interest alignment, whatever we are trying to do, whatever the regions are there here in this example 5 cross 4, but practically we are going to use 7 cross 7. So here the alignment is a bit different, right? So you try to make them as properly aligned. How can we align? Try to divide this entire region exactly, try to get the 2 cross 2. So once this proper alignment is done, then the features pooling can be done and it can be used further. So by using this, the overall speed of the architecture has increased because of this particular backbone architecture called VGZ 16 or AlexNet or whatever the architecture if you want to use it. So from the experimental results, if you can try to observe here, whatever the initial training time it took for the RCNN, it is trying to take 84 days, but 84 hours. But by using this particular fast RCNN, it has trimmed down to 8.75 hours only. The reason is pretty clear here that whatever the complexity of the CNN architectures has there, it has applied only once in the image. Because of that particular training for once, it has converged bit early as compared to the RCN. And also, if you can able to test for the inference time, in the inference time is also much faster as compared to the RCN. Now, what are the further limitations of this? Okay, now this is somewhat good, but what is the limitation of it? If you try to observe here, still this fast RCNN is dependent on some another model that is called pre-trained or conventional selective search algorithm, because here the regions we are not proposed and the regions are not adjusted. Sorry, regions are not trained. There the regions are simply adjusting with the help of little bit translation and shifting rotations. What if we can learn that regions also, rather than depending upon a selective search, if we can able to learn the regions with that idea, the third solution came, that is called faster RCNN model. So what are the procedures we have discussed earlier of the two algorithm? The same procedures are going to be followed here also. But the advantage here is that here the regions we would like to learn rather than depending upon a selective search. So idea is remains same. Take the image, use the backbone model in order to reduce that complexities. Now this particular backbone model, whatever the output we got it, instead of passing this to some of the selective search algorithm, let's try to learn the features with the help of the same losses. So whatever the feature map we got it, from this particular feature map, we can generate some different regions of various sizes. Then these regions can be learned with the help of the two things. What are the region your model has identified? What about the for that particular region, what is its classification loss and what is its bounding box loss? So in the previous case, these two losses were not there, but in the faster RCNN, these two extra losses is present, because here we would like to learn the regions here. So while in training this entire algorithm, how many losses we are going to get it? Total 4 losses are there. 2 losses for the region estimation and two losses for the, as usual, location and classification and location identification. So as you can able to see it here, from the given image, we got this 512 cross 20 cross 15 features. So here we are able to get n number of anchor boxes, as these bounding boxes or anchor boxes, anything will be fine. And for each and every anchor boxes, we are going to calculate the score. So in this particular score, as you can able to see, this is one anchor box, some size m cross n anchor box, and this is the anchor box we are going to get 1 cross 20 cross 15. For each point, we are trying to detect whether the corresponding anchor box is having an object or not, because it's a binary classification problem, right? Because just you need a box, anchor box or bonding box. In that particular box, whether you have an object or not, it's a binary problem. You're not going to recognizing what that object is. Just you're trying to worrying about that particular anchor box, the object is present or not. Let's take it again. Let me go back here. As you can able to see it here, what do you need in a given input image? There is a box object. This is the object is present. So in this particular anchor box, is there any object is present or not? If present, okay, fine. That anchor box is useful. If not present, there is no need to be get worried, right? But what type of that object is going to take care about these functions, because these functions we are already training for a particular target. But here the two different classes we are trying to use only to know for a given generated anchor box or bonding box, is there any object is present or not? That's it. So here we can able to consider this particular regional proposal network. This particular network will going to help you to know for a given bonding box, is there any object is present or not? Yeah. Again, we have a different number of sizes and shapes of the bonding boxes are there. So for this particular image, we can get k number of anchor boxes are there. So whenever you have a k number of anchor boxes, how many number of parameters to be learned? K into 20 cross 15 for the classification, and 4k into 20 cross 15 for the bonding boxes. These are the number of parameters we need to learn. So once you can find out many number of boxes, you can simply take the ranking of them, and you can take the top some number n number, and you can proceed further. That is the advantage of using this faster RCNN model. So here, by using this particular faster RCNN model, this is a much faster as compared to the previous thing, because here if you try to observe here, the size and shapes we are trying to, because location also you are going to learn here, the x comma y, this is also you are going to learn x comma y and height and width you're learning, and here the just classification of the object is present is not your learning. That means you no need to be get worried whether the object is perfectly located or not, because you are trying to make your model to learn the exact location also. That is also an advantage, right? So as and when this adjustment is not there, it is also performing much faster, even though you have two more losses. So as you can able to see it here, the inference time is much slower than the fast RCNN, because there you are dependent on the conventional approach, but in the faster RCNN, you are not dependent upon any of the conventional approach. This is completely end-to-end CNN model. But what are the limitations of this? Even though it is much faster, it is having two limitations. What are the limitations? It is a two-stage object detector. Why it is a two-stage? Because if you try to observe here, in the first stage, we are trying to get the regions with the help of some of the backbone architecture. So first stage run once per image, backbone network, region proposal network, because here first you are extracting the regions, but in the second stage, and those regions you are applying for the location and classification. So there are two stages are there. So this is called two-stage architecture. Then also you can have a doubt that this particular things is a binary classification, right? It's a binary classification. This purpose of this binary classification is that object is present or not. If it is present, what is its location? That is what we are trying to do it. Then also there is an extra loss that what type of that particular object is. That means unnecessarily you are trying to use 4 losses. Now, can we trim down these 4 different losses into finite number of losses, or what is the need of using 2 different classification losses, and what is the need of using 2 different regression losses? Can we solve these 2 by simply using only 2 losses rather than 4? Because here this is a two-stage architecture, right? This is one architecture, this is one architecture. Can we combine all these two together to get a single solution that is called end-to-end single architecture? Instead of two stages, it is a single stage architecture. That is with that idea, the concept came is called single stage object detectors. So whatever the classification and the regression is there, we are trying to do simultaneously in the single stage object detectors. If anybody have any questions, please let me know. I'll wait for a while. If you have any questions, please let me know. Okay. So in the previous case, as you can able to see it here in the object detectors. So object detectors. So here we are trying to use 4, right? Instead of doing this, let's only use two losses. One is for the classification, another one is for the regression. From 2 stages, we want to come to 1 stage, that is called single stage. How to do it? Because we also need to know whether the given bounding box is having an object or not. That is also a question, right? So in order to get that, we are going to use one confidence. Instead of simply using this losses, here we are trying to consider about a concept called confidence. So here let's try to do in the single stage object detectors. For each and every object, whether it belongs to the foreground or background, we knew it already. And we also need to know there are k number of bounding boxes are there. And we also know we have c number of categories, that is called type of an objects. Cat dog classification, there are 2 objects. If you're going to go for a 10 class problem, 10 objects. So C is representing about the number of classes. One is the including background. So total C plus one objects were present in my given input image. There may be a possibility for each and every bounding box. So in the previous case, like a region proposals, the region proposal network also we are going to use it here. But the thing is that what are the losses we are going to consider is bit different. So as we have said, we have C plus 1, that is called number of classes, and K is a finite K number of bounding boxes. Similarly for the regression problem. How can we achieve this? We have a different single stage object detectors are there, like YOLO, SSD, RetainerNet. So we have a different object detectors are there, YOLO, SSD. So RetainerNet here considered as a backbone model. So this is my image of color image 3 cross H cross W. So now we are going to dividing this image with grid sizes of 7 cross 7, as you can able to see it on the right side image. And for each and every grid, we are going to consider, or each and every bounding box, we are going to considering about the 5 factors. Initially 4. Now here we are going to consider the 5 factors, 5 parameters. What are those parameters? X comma Y, height and width, and its confidence, the presence of the object. Second thing, for as you can able to see, this is my 7 cross 7 grid. Here, what are the bounding boxes are there? Means what are the center pixel you are going to consider here? That is called base box. Here we are considering about for each and every center, we may have 3 possibility of the bounding boxes of different sizes. Not necessarily 3, you can go for 5, 7 or n number. Many number out there, but for the easy understanding, we are considering about the 3 here. So the total number of possibility of the bounding boxes here are 7 cross 7 cross 5 into B plus C. See here you are going to considering about the 5 is my 5 parameters. B is my, for a simple object, there are different possibility of bounding boxes can be there. In this case, we are considering about 3. You may consider 2 also, not a problem. Plus C, that is called the type of the objects are, as we have seen earlier also, cat, dog, background. Now to train a model, you need to prepare the training data. How this particular training data can be prepared? As you can able to see it here, as initially I said that the C is representing about the confidence, width and height, center pixel, and type of the objects. Categories, probability of cow, probability of dog, and so on, truck, and so on. So we have a different categories are there. Those being a number of information we can able to consider. Maybe in this case, we may can consider about the one hot encoding. How? Maybe you can take an example. Let's assume we have a 3-class problem is there. If that particular this particular bounding box you might be considering as an object, that is called a dog category, and this particular feature can be represented as CWH X and Y. Wherever the dog is there, you can keep it as a 1. The rest of the page you can keep it as a 0. Similarly, there will be another category. This is, let's assume this is a car category, for example. Instead of cow, you can consider as a car. In that scenario, height and width at CW are common for that particular object. Wherever the car is there, that particular part is 1, the rest of the information is 0. Why we are trying to use one hot encoding concept here? To easily calculating about our losses. That is the advantage of using this. So whatever the image is there, we are going to dividing into 7x7 grid. As you can say, divide the image into 7x7 grid. For each cell, we have a 5 different values that is called C, W, H, X, and Y. And K quantities is nothing but here we have K number of number of classes you can consider. So here we are trying to calculate the probability of confidence of each class. So here we need to take the help of these all parameters to estimate. So what are things we are trying to estimate? Because whenever you're trying to talk about this particular number of possibilities, we can have a many number of possibilities are there. So many number of possibilities are there. And at the end, we need some possibility in this way. Whatever the probability of the cell is there, if the object is present, then it has to look in this way. How can we achieve this? Our target is to achieve this, because if you can able to see it here, this is cycle category, dog category, car category. This is something background. Because each and every cell is trying to talk about some information, right? So now we need to analyze for the each and every cell, then we need to take a decision. There could be many number of possibilities are there. By using some non-maximum suppression concepts, we can achieve this. How to do it? Let's have a look. Now, as we knew, the given bounding box have some values that is called X, Y, W, H, and C confidence. Anyway, confidence we have. Now we need to train, right? Because this is a regression type problem. So we also need to compare with our ground truths. How can we compare? Because X minus X is mean square error type. So X predicted and my ground truth. What would be the difference? Y minus Y predicted. What is the difference? And so on. So we are trying to minimizing this all the losses, because whatever the bounding box it is you're trying to identify, it has to be close as to your ground truth. Then only the losses will be lower. So whenever the losses will be lower, that means your model got the proper prediction. Now the further question is that whenever the object is there, then it's fine. Whenever there is an patch, there is no object is present. In this example, there is object is not at all there. So whenever the object is not at all there, then what is the need to learn the extra parameter? What are the parameters like X, Y, H, and W? Do we require to learn this? Just we no need to record anything, just we need to minimize the confidence only. So whenever there was a bounding box where there is no object, so we no need to be trained rest of the thing, just we can take to minimize the confidence only. So by combining all these factors, we can train our models to get the desired output. So as you can able to see it here, as we have said earlier also, each and every box may have 3 combinations or 4 combinations, depends upon that, right? We have already considered about this 3 combinations or 2 combinations, whatever it may be. So while you're training, how we can able to pass the tensor? Let's have a look. Here the B part is, right? So in this example, B considered as a 2. So let's see, the first values are probability of the confidence. This probability of object is nothing but confidence. For the first bounding box, corresponding X, Y, height and width. But the first same position, we have a two bonding boxes. For the second bonding box, confidence, XY, height and width. So last one is called, as we have a k number of objects are there. That's called C number of objects are there. For each and every object, what could be its confidence? That is called probability of cat belongs to the object, probability of bird, and probability of TV, and so on. So this is my tensor. So we are trying to learn this tensor, because here for each and every center, we are going to consider about a finite number of bonding boxes are possible, because we don't know the shape of the object, shape and size of the object. That is the reason in this example, we are considering about the two bonding boxes. You may can increase this 3, 4, 5. So when and then we are going to increasing the number of assumptions, then the complexities are going to be increased. So once it is features have learned, then the last step we are going to use a non-maximum suppression. So what is meant by non-maximum suppression? Let's have a look. So by using this is a YOLO concept, the single object detector. So this is much faster as compared to the previous things, because not only training is important, also in the testing. The testing is also very important factor for us. So inference time, how fast it is. So YOLO is 45 frames per second as compared to the other object detectors. Now the things are fine here, but now the challenging question comes here is that, as it is an object detector, till now we are talking about the bounding boxes and all. If it is a classification problem, simply we can use some of the loss functions, right? But here the bounding boxes are there, and the ground truth and bounding boxes, how can we calculate the performance measures? So in order to get the performance measures, how robust your algorithm is, instead of simply using a mean square error and so on, we are trying to calculate the performance measures with the help of the IOU. That is called intersection over union. So as you can able to see it here, the green color part is a ground truth which we have drawn, and the blue color part is your model has got predicted. So how can you calculate the IOU? So IOU is nothing but area of intersection over the union. So this is IOU. So in this example, the IOU is 0.54. If the area of intersection and the area of union is as close as to each other, then the IOU value will be almost equal to 1, right? So even whenever your predictions are as close as to your ground truths, your IOU value will be increased, right? So whenever the IOU is 70% is somewhat good. If it's a 90%, it's almost perfect, but we are expecting 99 or 100%. It is challenging, but we can achieve it. So here in this particular object detectors, we are going to calculate the performance of the model with the help of the IOUs. Now here you can see different algorithms. They are going to consider about the thresholding of IOU. The intersection over union can be, you may consider about the 30%, 40%, and 100%, and so on. As and when you are going to considering about the 100%, that is an extremely robust algorithm, but achieving that is very challenging. Now the another important problem comes here is that now you can see there are many overlapping of bonding boxes are there. How we can able to filtering out? There are many bonding boxes are there, right? That is where we are going to use a concept called non-maximum suppression, as you can able to see it here in this example. So there are many possibilities are there with the help of this training procedure. Many possibilities are there, but now here we need to reduce somehow, right? So in order to reduce it, we are going to use the non-maximum suppression so that it can able to get the finite number of detectors. So what is the meant by non-maximum suppression? So the name itself is talking about what other things are not having any maximum value, simply you can ignore it. Non-max suppression, right? So now you see how the things can be done. So here you can able to observe there are the two bonding boxes are there for this particular puppy. There are two more bonding boxes are there. So total 4 are there. Let's try to calculate the intersection over union within the detected bonding boxes. So let's try to do the IOU between the blue color and orange color, as these two are almost related to each other here. Here the 0.78. Similarly, you can do the corresponding IOU with the blue color with yellow and velvet. So you got the different IOU intersections. because here the previous IO is 0.9 and another one is 0.8. So third one is 0.75 and 0.7. So instead of blindly doing in a shorting way, better we can calculate the intersection over union, wherever the values are not maximum values, we can simply suppress it. So the second part, we are kind of able to do the non-maximum suppression between this yellow and the velvet, where we got 0.74. So we can able to remove the rest of the part. So here we can use some threshold, right? So wherever we are going to use some of the threshold, whenever we are going to get the higher threshold, we can able to use those things. So that's called non-maximum suppression. Now this particular algorithm, will it going to work on these type of samples? So whenever we have a sample like this, many number of objects of different sizes, small objects are there, but the number is too much. In that scenario, is this non-maximum suppression will going to work? Because in this case, finite number is there, so somewhat it is good. We can do this. But what if this particular case? So here the non-maximum suppression may not going to useful. So the still the research is going on in these aspects. Whenever we have a crowdsourcing or tiny objects, we are going to head counts, we are going to consider, then this challenge still exists. The things are just going on. So as of now, if you have any questions, please discuss. Otherwise, one practical thing I will show you. No, not this one. So let me show you one samples, then I'll wind up. So this is one application just for your reference. Just we have calculated trained model on one data set. Here, this problem is having a 5 class problem, and in the underwater, starfish and water weeds, and there are 5 classes problem is there. These are all the raw images, as you can able to see it here. Few images I'll show you. So these are all the raw images. Of course, as it is underwater, it is having many challenges are there. It is not properly visible and all. So these are all the underwater challenges. So whenever you would like to do any of the object detectors on this, of course, yes, the pre-processing step is we have to enhance the images. And then we have to label the models, like you have to do, sorry. So these are all the bounding bosses we are going to create, because these are all my ground truths. Because the first one is called a category. What are the class the particular objects are present in the given image. Let me open all this together. Raw data, first one. Here there is the starfish is present here. Of course, it is not that much clearly visible here. There are starfishes are present, and these are all the corresponding ground truths as we have discussed just now. These are all the some of the ground truths here. The type of the object and its corresponding height and width and center and all. And once you train your YOLO models, these are all the outputs we can able to get it. So as I said, there are 5 categories are there. These are all the problems which it has detected. Some images with the good looking we will see. Yeah, hit the starfish 4304. Okay. So this is the image with starfish. The 4304 original image. Let me show you. 4304. Yeah. So this is the original image. As you can able to see, there are a few starfish we can easily able to detect here, but as and when it is underwater image, it's very difficult to detect properly. So some basic pre-processing is required to detect. So the number is 4304, right? 4304. Yeah. So these are all the corresponding labels we have. There are 5 labels were present. Once your model got trained, these are all the outputs you got it. Of course, yes, this model is not properly trained because of the just for sample we have trained the model, not for the application oriented, just to show you. what type of images or what type of object detection can be done. So as you can able to see it here, there are different categories it has detected. That's the water well. This is a second category. There are two starfish, but in the original image it is not visible, right? After doing a simple pre-processing, we can able to get the proper detection. Of course, yes, this research is still open. We're trying to integrating different solutions to provide an end-to-end solution. This is our simple sample. This model here we have used as a YOLO version only, one of the YOLO, to detect these objects in the underwater. Yeah. So what are the questions? If you have anything, please let me know. Or just give me a minute, just I'll be back. Meanwhile, if you have any questions, please put it in the chat box. Just give me a minute.
So you may ask if you have any question. Dr. Viparthi is with us. Please feel free to ask if you have any question, because the session is about to end. Yeah. So yeah, Mallika Shri, you can write your question.
Yeah, sorry for the delay. So this is a one different type of object detectors, and it can be widely used in many places. For example, in the smart cities. For example, one small problem we are working for the state government here. That is called garbage detection. For example, garbage detection is one area where this object detector concepts are widely useful. And also you make an estimate a smart city, how many number of old houses or how many number of new constructions are happening. I mean, we can use this type of object detectors for different applications. And just I'll show you two more slides and I'll wind up here. But what are the object detectors we are going to talk about now? All the object detectors with the train weights may not going to be useful whenever they are going to change the application. It is an object detectors only. There is no doubt at all, right? But if you will try to see these two, these are two different, challengings. One is a conventional view, like the way we have discussed just now. Another one is a aerial view. So here the same algorithm may not going to work. So yes, there are many, researchers are working on it to handle this multiple challenges together, whether it can be aerial view or whether it can be conventional view, because of the diversity in the object shape and sizes. So the still the research is open. If anybody interested, just to make an, if you want to have a look, you can please visit us. So in recent time, very recently, there is an architecture which is proposed by, I think, Meta, that is called segment and track, anything, SAM track. The name is called SAM track. And almost this all the object detector concept they have resolved. Of course, yes, there are few still limitations also there, but majority of the application it is trying to resolve. In the aerial view also up to finite size it is performing well, but whenever it is going to be a very tiny, then that particular SAM track is also having some limitations. So if anybody interested, maybe you can have a look into it. Yeah, if you have any questions, please ask. Slow RCN. What is meant by slow RCN, by the way? Why the RCNN is slow, or what is meant by slow RCN?
Sir, the features are not, the regions are not like processed by the model, that I understood, but the difference between slow and, that's the only difference between slow and fast RCNN.
Okay, no. That is not the difference between slow and fast RCNN. See here, from a given input is there are 2000 regions are there, right? We are identifying the 2000 region. For each and every region, you are applying a CNN algorithm. I mean, whatever the region is there, that means your convolutional algorithm, CNN architecture has trained 2000 times. So one architecture required 134 or 100 million parameters. Then this particular architecture has trained 2000 times. So it is very complex. That is why it is slower. But whereas in the fast RCNN, we haven't trained that to 2000 times 100 million parameters. We are not going to use it. What we are trying to do, we are trying to make a small change. What is that? We are going to use the backbone, because what is the importance of using the CNN architecture? First of all, because CNN architecture can properly able to recognize the object. That is the intuition, right? Because as you knew
Yes,
the
sir.
difference of tradition. So please. Yeah, please carry on. Yeah. So what is the basic principle of CNN algorithm? The CNN algorithms, instead of simply extracting the features, it is going to learn the features from the given input data. That is already you are aware of it, right? So here, instead of training or using this architectures 2000 times, let me take the advantage of the features by using the backbone. So what are the image is there? I'm going to use the instead of 100 million parameters, let me use 80 million parameters. That means the architecture is divided into two parts, like this. Like this. This architecture is divided into two parts. Let's assume this particular part is having X number of parameters. These are all the Y number of parameters. Let's assume the X number of parameters are more number of parameters. So what I'm trying to do now, that this particular architecture I'm going to use it as a backbone. So that backbone is this. So once I have applied this on an image, I already got a feature vector that is called latent features. I already got it. Latent features, for your easy understand, let me say that from a given input image, wherever what is the background, what is the uniform information, where is the non-uniform information, and so on. That all information we already got it from the CNN architecture. Now, whatever the image our response we got it, and upon that we are going to run a tiny architecture 2000 times. So you no need to train the entire complex architecture 2000 times. We are dividing into two parts. That is a fast RCN. Other than that, the procedure is remains same. Only where we are applying the CNN is only the difference. So in the fast RCN, immediately on an image we are applying, getting features, apply for the region proposals, then last finite number of layers you can run so that the model can be fast. That is the difference.
Okay,
Yeah.
sir.
If anybody have any questions, please discuss. Yeah. So if anybody have any questions, if you would like to meet or interact, you can mail me, or you can visit our website for quick reference of what type of work we are working. If anybody working in the similar areas, maybe you can feel free to reach us.
So thank you so much, Dr. Viparthi, and I
Ma'am,
believe
if time is there,
participants.
I can explain some of the algorithms. If time is not there, I'll wind up.
Yeah, so I think because the next session will start at 5. So
Yeah, please. Yeah.
stop now. So if you have any question, participants, you can quickly ask. Otherwise,
Yeah.
we have to stop now.
Yeah. If anybody have any questions, you can feel free to reach us. You can send me an email or reach me what are the ways we have. Then
And
we can have a discussion.
if you all can switch on your video, then we can take a picture with Dr. Santosh. You can unshare this, please.
Oh, sorry.
So thank you so much, Dr. Viparthi, for joining us and telling participants about details about object detection, because this is one of the relevant area, and I believe motivated with your talk, the participants will be finding it interesting and they will work more in this direction. Thank you so much.
Thank you, ma'am.
Please switch
Thank you
on your
all.
video quickly so that we can take a picture before we end this session.
So participants, if you need any data sets, somewhat things, you can reach us so that we can provide that free of cost. No issue.